Hi, thank you, Oz, for having me. My name is Levi Broderick. I am a developer at Microsoft. I've been working on .NET code since 2007, so it's been a while. Previously, I was on the ASP.NET team back when System Web was a big programming model for ASP.NET. Around the 2011-2012 timeframe, I became one of the primary security developers on ASP.NET. So bumped around there for a few years. Eventually, I took a small hiatus from .NET and went over into the Windows org and Xbox to work on some hardware security related projects. But now I'm back in the .NET ecosystem, kind of where my heart is. And I've been working on the base class libraries and .NET runtime team. So system string and friends like that are kind of my wheelhouse now. More recently, I've also been focusing on security from the perspective of API design, the perspective of how do we make sure that the libraries that we give customers that they lend themselves to a pit of success rather than a pit of failure. Another way of looking at that is if you're a developer writing .NET code, how hard do you have to think about whether what you're writing is safe or what you're writing is dangerous? Ideally, we would like to be in a world where all of the code that you write is correct, is able to be deployed across your enterprise without too much concern about any security consequences that there might be. There are, of course, failures that we've had over the years, but my goal and the goal of the people that I work with is to try to get us into a better state and to try to get the ecosystem into a better state. That said, this presentation isn't going to be a typical presentation like you'll see at places like OWASP. Those presentations, when you talk about ASP.NET applications, tend to focus on authentication, authorization, preventing cross-site scripting, things like that. I wanted to focus from the perspective of writing business logic, writing libraries, things along those lines. If you're writing code that takes user data and does something with it, separate from displaying it in an HTML page, you're just running some logic over that data. How do you know that the logic that you're writing is correct? How do you know that we're not inadvertently introducing holes into your applications? This is actually interesting from the .NET library perspective as well, because on the .NET team, we write libraries, not applications, right? We write the building blocks that you use to write your own applications. So when we're reviewing components like system text JSON, the new JSON stack, or ASP.NET Core, we have a series of things that we're looking for ourselves. And I wanted to take this time to share some of that with you, along with some common pitfalls that we see and how you might encounter those in your own code review and address them in your own code. The thing that really sticks out as something that I want people to take away from this is understanding when a piece of data in your application or in your library is untrusted. Now, what do we mean by untrusted? We mean that the data is not something that's shipped with the application or shipped with the library itself. The data came from an external source. The external source is often a client, such as someone on the other end of a web request. Maybe it came from a file system, maybe it came from the database. And as a library or application author, it's up to us to make a judgment call on whether this data is trustworthy. So if I'm a web server and I'm receiving data from the client as part of a query string or part of the form body, like that data is pretty clearly untrusted in the sense that I need to perform my normal business logic validation over it. There might be some exceptions carved out here. Maybe I know that the data is coming from my trusted front end rather than from an arbitrary location. In that case, I might implicitly trust the data and only perform some quick sanity checks over it. If you're following defense in depth practice, generally you would treat all data into your application as untrusted, even if it came from the database. It's possible that someone tampered with your SQL database. For most applications, though, this isn't an absolute, it's definitely a shade of gray. So what I want to go over now is what kinds of places might you encounter data where you have to make a potentially non-intuitive trust decision? So here are some examples, just taken from various websites that I scraped. So the example at the top is MSDN's documentation for system.string. The example in the lower left is if you use Bing's reverse image search feature, that's the UI that's displayed to you. The example in the bottom right is Twitter's create account page. Now, the reason that I like this is that there are lots of examples of how untrusted data might actually flow into the application. The more obvious ones might be the URL or the actual file upload contents when you're doing a reverse image search, or even the form field inputs such as a username or phone number in Twitter's user registration. But for some examples of good non-obvious untrusted data sources, I want to point out how you use the data actually matters. In this case, the URL string, I'm dividing further into different subcomponents. The first component, en-us, that occurs in front of lots of different Microsoft URLs, well, that's the culture that's going to be used to render the contents for your display. Now, when I browse it, I'm en-us because I'm an English speaker located in the United States. It might be fr-fr, it might be es-es, and so on. Now, one immediate question is, how does this translate into application logic? Is the application using this particular part of the URL as a path on the file system? Is it actually looking for a specific folder on the file system called en-us, or a specific folder called netcore-31? And is it looking for contents underneath that? If that's the case, then maybe you care about things like path traversal. But from a library perspective, we also care about what APIs you pass this data into. One obvious, air quotes, thing to do might be to take en-us and pass it into cultureinfo.getCultureInfo. And that will return a culture corresponding to US English. Now, that is interesting, but it also opens up a potential hole inside of your application. What happens if you pass URLs like this into the server? There are thousands upon thousands of different combinations. A lot of these cultures don't actually correspond to anything that we have built-in defaults for. But if you pass in, for instance, en-ac, you're going to get a generic English culture. So why does this matter? Well, does your application cache these pages, cache this content? Is it possible that if I'm an adversary and I just make these kinds of requests over and over and over again, that I'll end up flooding your application's cache and making your web application fall over due to an out-of-memory failure? So things like that are what I really want to focus on for this talk. Another example is Bing's reverse image search. The example that we brought up earlier was, okay, the actual file contents themselves that you're uploading, sure, that's untrusted. But what about these other considerations? The file name is transmitted in addition to the file contents when you deal with a file upload control. Are you storing that information anywhere? Is it potentially being used as the file name on something that's being written to disk? Remember, that file name is character by character controlled by the adversary. It can include quotes, ampersands, escape characters, and so on. Even if you're including that file name in a seemingly innocuous place, like a JSON request or response body, well, make sure that you're escaping it properly for that scenario. Another example is, hey, I'm using an image processing library in my application. Well, is your library up to date? Are you subscribed to security notifications for that library? Make sure that your third-party dependencies don't become themselves an attack vector into your application. The URL case is also rather interesting. There has been a recent spate of attacks using a mechanism called SSRF, server-side request forgery, where say that I know that you, the front end, can communicate with a backend server some backend hostname, something that's behind your firewall. I don't directly have access to that, but if I give the front end the URL corresponding to that backend server, will the front end happily make a request to that server, pull down data, and then process that data? In various cloud hosting services, there are administrative planes which have secret but well-known URLs, just some 127 dot whatever IP address. Nominally, I wouldn't be able to access that from outside of your firewall because I can't route to that IP address. But if I can convince your application to make a request to that address on my behalf, I can start potentially influencing how your application runs or other administrative services. By the way, I have a lot more listed in the speaker notes for these slides, and I'll make these available after the talk. So you can go back and you can look at URLs that I'm linking to, sample MSRC cases that we've seen, and so on. There's a whole ton of resources there. So how do we approach code reviews? Something that's kind of interesting is that as security professionals, we sometimes have trust issues. We always want to catch the bad actors, but the reason that that's such a rewarding process is that people acting badly are actually an exception rather than a rule. And it kind of makes sense if you think about this, because society as a whole, if people just stopped following laws, if people stopped following traffic regulations, society itself would just kind of screech to a halt. And the fact that things just, for the most part, continue to work is actually pretty good evidence that, you know what, most people actually want things to work correctly. Most people want to participate in a valid and well-intentioned manner. When we're talking about applications or libraries, we want to assume that the majority of things that we're going to be processing are actually well-intentioned, and we should optimize for those cases. That also means that we should potentially not optimize for failure cases, but we also don't want to fall over dead. We want to make sure that our applications behave correctly, even in those circumstances. Normally, let me actually go to the next slide and then I'll come back. Normally, when we're threat modeling an application, we would use a tool called the threat modeling tool, which creates this lovely Visio diagram of all of the different data flows from your application to external resources like the file system, like the database network. Well, we write libraries. If you were to produce a threat modeling diagram for our libraries or components like system.string, the threat modeling diagram is literally a circle. We don't have trust boundaries because we run inside of your application. We trust you implicitly. You have the ability to stomp on our memory and overwrite it if you really wanted to. So what we do instead is we enumerate resources that we're trying to protect. Some of those resources might be hardware availability resources. We want to make sure that we are still available to applications because we have enough network bandwidth to respond to them. We have enough CPU to respond to them, and so on. If we're processing customer data, the confidentiality of that data is also important. That's a resource that we're trying to protect. If we have data that we process internally and that data is stored in a database file system somewhere else, we want to make sure that that data also has good integrity. This is not an exhaustive list of everything, but it does give the impression that many of the problems that tend to afflict .NET applications tend to be under the denial of service category. They tend to affect the availability of one of these resources. From the .NET perspective, when we talk about MSRC cases, and don't worry, code's coming up pretty soon, we tend to bucket failures into one of two types. The first is failures due to logical errors on our part. There was a plus in the source code that should have been a minus. There was an if check that evaluated incorrectly. We were missing a bounce check. We had an off by one error when we were iterating an array. In managed code, these errors tend to manifest themselves primarily as denial of service, as I said earlier. But depending, they could also manifest themselves as elevation of privilege, spoofing, things like that. That's definitely the rare case, but it does happen. The other nice thing about these logical errors is they're easy enough to fix, both from our side within the framework and from your side as library vendors, because the the behavior that is undesirable is unintentional, and pretty much everyone agrees that that behavior is buggy. If we let someone into the system who we shouldn't have let in, that's a bug. We can fix that without breaking anyone. No one really takes a dependency on those buggy behaviors. The other category is design errors, where we have a component that is behaving as it was specified, like we actually spec'd it, looked at the spec, said, yep, that is what we want it to do. And we didn't realize at the time that that behavior was actually insecure. In order to fix these kinds of things, if we decide that we need to ship a patch, that often involves removing the feature of the product that was dependent on that behavior. Now, if we're talking about removing features rather than just fixing bugs, this clearly has impact on applications, on components that depend on us. And in those cases, that's when we tend to, wring our hands and kind of pace the room nervously and say, hey, if we ship this, will your web application just fall over dead when they install the patch? These patches are often very, very noisy. One example of that is a few years ago, we shipped a change to ASP.NET Full Framework that forced enable viewStateMac to be true, even if your application had explicitly set it to false. The reason for this is that there was a misdesign that encouraged people to set that to false, and we actually documented for these scenarios you will want to set this property to an insecure value. And it wasn't realized at the time that that actually allowed code execution inside the process. In order to shut that down, we broke a lot of applications. And this is a situation we want to avoid. And that's why when we talk about these kinds of security checks, these kinds of API reviews, we're really focused heavily on those. How hard is it to misuse an API or a library? So this and then code. The overwhelmingly common attack that we see in libraries or in business logic involves algorithmic complexity attacks. The adversary is going to send O of n data to the server. Maybe they send 2 kilobytes to the server, but we perform 4 million units of work. They send 128 kilobytes to the server. We perform 16 billion units of work. This affects availability of the application. If we're busy spinning CPU or taking all of the memory, your application's not available for legitimate requests to be serviced. And you're also stuck with the cloud usage bill. As you deploy your applications to a place where you actually have to pay for electricity or pay for CPU, people attacking the application by exhausting your CPU are costing you, real world money. So demos, because I don't just want to stay in slides the whole time. So the first thing I want to do is let's talk about algorithmic complexity attacks. Let us talk first about string.replace. So string.replace is a method everyone's used over and over and over again. Given this input string, I want to find every lowercase l inside the input string and replace it with an uppercase L. Let me run that once and see how long it took and see how much memory it took to do that. So it allocated 88 bytes. It consumed 88 bytes of memory in order to perform that operation. That's just the overhead of the string plus a few closures that I had to set up to some fixed overhead that I set up just to run the test. And it took, a fraction of a second. Nothing terribly interesting there. Let me actually, oh, hey, I can actually zoom in and make the text more legible. Awesome. Now that's all well and good. String.replace is not terribly exciting on its own, but what happens if you have a system where you're actually doing the replacement based on adversary provided input? Say that you have a code editor or a text editor based in the cloud. So someone is doing a search and replace inside their file. So they control the contents of the file, which in this case is the input. They control the string they're searching for, and they control the string used to replace it. In this case, the string that I'm searching over is 30,000 X's, and I'm replacing each X with 30,000 Ys. If I were to send this to the server, it would look like input equals lots of x's and search for equals single x and replace with equals lots of y's. That string is a total of 60 kilobytes long. There are 30,000 things here, 30,000 things here. So the entire request payload fits into 60 kilobytes. If I run that, so again, this thing at the beginning was a regular string.replace. This block right here, this second block on the screen, was the string.replace that took place over the adversary provided input. They provided 60,000 bytes worth of input, but we did 60,000 squared units worth of work. And you can see here we allocated almost 2 gigabytes of memory in order to service this and took 1.5 seconds. If your application has any type of memory throttling on the web server, like that could potentially and crash your application. Or in this case, it took 1.5 seconds to process. Well, that's 1.5 seconds where you had a core, an entire core running at 100% throughput. If you're running on a 16-core web server and 16 of these requests came in at the same time, you're now going to have to wait 1.5 seconds before you can process any legitimate requests that might come after this. Some more things to keep in mind. So that's string.replace. Oh, I guess I should actually show you the code that I have for string.replace. It's literally calling string.replace inside of a helper method that just records information about the GC and then prints things like how much time it took to execute it. This code will be made available along with the slides, so don't worry too much about that. Okay, so that's string.replace. So, okay, now string.split. So in this case, what I'm doing is I'm mimicking sending a payload 7, 7, 7, blah, 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 4 megabytes of that payload to the server. The reason that I chose 4 megabytes is that 4 megs is the default ASP.NET request size. And what I'm doing is I have a piece of code that's literally just string splitting that, converting them back all to integers, and then summing all of them together. If I run that, keep in mind I'm mimicking sending 4 megabytes to the server. It took 83 megabytes of memory in order to service that request. And there were some number of collections that took place. Now, this is not really an algorithmic complexity attack. And the reason that it's not really an attack in that regard is that I'm still doing O of N work in response to an O of N request coming in. A 4 megabyte request came in. I'm doing 4 megabytes times some constant factor worth of work. That's how string.split works under the covers. Now, one thing that could be interesting though is, hey, if taking 80 megabytes of memory is unacceptable for your application, then you could potentially start using features like span of T that came in .NET Core in order to lower the amount of memory that you're using. The spanified version of this basically contains pointers within that string. I say pointers, but it's actually fully type safe. It says, hey, here is the data that I have left to read inside of the string. Let me find the first comma inside of that data. Here's the contents of the string up to where that first comma exists. Let me pull the integer out of that, add it to the sum, and then reposition the span just past where the comma was. If I now run this sample, remember I'm sending 4 megabytes to the server. I'm only allocating 40 bytes of overhead as opposed to 83 megabytes of overhead in order to service that. The total time that it took to run the operation isn't significantly changed. It's only half. That's a good indication that this is an O of N instead of an O of N squared operation. But it still gives you a good idea of how all of that works. The final thing that I wanted to show is this is actually an MSRC that we had a few months ago that we fixed. In this sample, we are parsing a data structure. We're parsing a length prefix string. In this case, we have a 32-bit little Indian integer that says, hey, the string that follows me is 5 bytes in length, and it's the phrase hello in UTF-8. The implementation of this is pretty straightforward and says, okay, let me read the 32 bits that corresponds to the length of the string that I expect. Let me allocate a byte array to hold that, and then let me keep looping until there's no more data, and then turn that thing back into a string. If I run this, it does what you expect. There's some fixed overhead for all of the operations, and the string was hello. All well and good. I can change this, and I can say, okay, instead of 5 bytes, show me, it's 2 bytes instead of 5. What this code's going to do is it's going to pull out only the first 2 characters and then say that's the string that you gave me. Now, there is actually a bug here. The bug is this stream ostensibly is adversary provided input. We're reading some count directly from it and then making an allocation based right off of that account or right off of that amount. So if as an adversary, I tell you there's actually around 1 gigabyte worth of data, this is something like that. It's around 1 billion in little endian. If I now run this, sorry, 2 billion, not 1 billion, because I can do hex math. It's now eagerly allocating a 2 gigabyte array based on what the adversary provided. And this is another case where, hey, if you're using user input in order to provide the initial capacity for a data structure, be aware of the fact that they could get you, they could try to your application. Like I said, this was an MSRC that we had. We fixed it a few months ago, and I have links in the slides for what the, sorry?
Is it okay to ask a question? I have a doubt.
Yeah, go for it.
So you mentioned that this was an MSRC.
Yes.
But my question is normally MSRCs don't look for denial of service. They only look at memory corruptions, most often only out of bound writes.
Not always.
With MSRC, so.
Yeah, so sometimes. The reason that that's a good question. The reason that we care about denial of service attacks is that we are the platform, we are the web server, for instance, IIS, ASP.NET, Kestrel, and so on. We run our code before application logic even has a chance to run. We had almost this exact code inside .NET that was running before your own application logic was able to run. So the idea is if you could send a specially crafted request to the web server and trick us into ooming, your application now becomes unresponsive because we remain unavailable to service legitimate requests. Denial of service attacks tend to have a different vulnerability rating than things like information disclosure, remote code execution. But when the DOS is inside of our libraries, the libraries that we ship worldwide, we do definitely care about it.
Okay.
And especially if you, the application developer, don't have control over the fact that the code's executing. That's the thing that really makes us nervous.
Okay, so basically you mean to say the default configuration that you have and not the user modifiable config that any user can do. Is that correct?
Yes, correct.
Okay.
Yeah,
Thanks,
if we provide any type of configuration, we try to make those defaults safe. But if your application modifies that configuration in a manner that we deem unsafe, then we're not necessarily obliged to fix that.
Obliged to fix that, right?
Yep. Yeah, so this is just a quick summary slide of what I went over in the demos. There are also APIs in .NET that are more susceptible to DOS attacks. Type.getType, it's very popular for especially serialization libraries to pass or to call this passing a user-provided string as input. That is a recursive method. Recursive methods can stack overflow. If you pass some untrusted string in there, it will definitely crash your application. Binary formatter and friends fall into the same bucket. Even if you've applied a serialization binder, there are still payloads that will crash your application. Cultureinfo.getCultureInfo, remember that thing I mentioned earlier, falls into a slightly different bucket where cultureinfo.getCultureInfo has a static cache that they keep adding to every single time you pass in an unknown string. If that bucket keeps growing over the course of your application, it will eventually start consuming megabytes, gigabytes of memory, because static caches generally tend never to be cleared until the application resets. By the way, a quick note on loops, recursive methods, and so on. There are some interesting things that you have to be aware of when you're deserializing data. What I have here is a sample application that prints an org chart for your employees. It reads this JSON payload. This corresponds to an employee object. An employee has a name, an ID, and a manager. So the lowly worker bee has a manager of mid-level management. Mid-level management has a manager of big corporate boss. What this application does is this application is deserializing using newtonsoft.json, and there's a reason I'll get soon as to why I'm using newtonsoft as a deserializer. It deserializes that payload into an employee object, and then recursively prints out A reports to B, reports to C, and then how many steps there were from the initial object to the CEO of the company. And again, the employee definition, name, ID, manager. So here is the payload that I'm going to run it over. Set a startup project and run. So exactly as you expect, the lowly worker bee reports to mid-level management, reports to the boss, who reports to nobody, except for maybe the shareholders, I don't know. And then the lowly worker bee is 2 steps away from CEO. Well, okay. What if I choose a different payload? What if I do this one? This is a few hundred kilobytes of you reporting to you, reporting to you, reporting to you. It's a very, very deeply nested object. If I run that through the system, it's kind of hard to tell, but the thing that was at the very, very beginning here was a Stack Overflow exception due to the recursive method call. This is the other part of looping and data structures that's somewhat dangerous inside of an application. If you're recursively calling into a method and the recursion depth can be specified by an attacker, it's possible that after a few thousand calls, they could Stack Overflow your application. And remember, Stack Overflows cannot be caught in .NET. They are immediate process termination. Now, one way that you might be able to resolve this is to say, well, for something like JSON.NET, let me just set the option that says, hey, I'm going to limit the maximum depth that the deserializer will deserialize, so 100 items. If I run this again, it will still throw an exception while it's deserializing, but the exception is different. It's not a Stack Overflow exception. It's something that just went off the screen. It's a JSON exception that can be caught. Your application will respond with an HTTP 400, and you'll just keep going. Like you're still able to service the next request. So that's all well and good. That's one way to avoid this issue. But now comes into why did I choose JSON.NET? Well, JSON.NET by default has this behavior where it can create cyclic object graphs while it's deserializing. In this particular case, what I've done is I've crafted the payload so that the lowly worker bee reports to himself. And what happens if I put this into the same application that I have here? I'm still limiting the max depth to 100. What happens when I run this? So it's running and running and running. You saw it was printing over and over and over. It printed a few thousand times because it executed the method a few thousand times. Because remember, it's a recursive method. And eventually, where are you? Where are you? Boom, Stack Overflow. The application is crashed at this point. even though you have set the JSON serializer settings to what you believe to be an appropriate maximum depth. This really comes down to when you're deserializing data, especially something that can influence how you make recursive calls or how you make looping calls. Just be very, very careful with how you actually operate on that data. Perhaps set the JSON serializer settings that says don't allow cyclic graphs if you're not relying on it, or change your algorithm to use a loop rather than a recursive algorithm. By the way, the naive way to write this using a loop is also vulnerable to an infinite loop problem. I have sample code demonstrating that problem that I won't get to here because I don't have time, but it'll be available for people to look at afterward.
Levi?
Yes.
So you mentioned like the application, like the Stack Overflow, you just go through that, right? But does it ever lead to stack corruption? And can that have an effect?
Good question. Stack Overflow in .NET will not lead to stack corruption. Stack Overflow simply terminates the process. It's actually, in .NET, it's very, very hard to get stack corruption unless you fall down to unsafe or native code.
So like if you have applications like Microsoft Power BI and all those, which rely on .NET, so on some .NET libraries, then getting a stack corruption in that would be something that's like difficult to do, right?
If you're operating in normal managed code, normal type-safe managed code, stack corruption should be ideally something that would never happen. If I were an adversary looking to cause stack corruption, I would target methods that were annotated with unsafe or that used pointers or methods that p-invoked into native code. Those methods tend to be the things that could have stack buffer overruns or caused unbalanced stacks. But the nice thing about that, though, is it gives you a target of what methods are interesting from a review perspective, basically methods that use pointer arithmetic. So that's about looping, recursion, deserialization. The other thing that we see are incorrect optimizations. I had mentioned culture_info.getCultureInfo earlier. Your static cache, if you continue building to it, even for failure cases, could be an attack vector in that it can potentially never get cleared. Span and ArrayPool are also kind of interesting. And the reason for this, I have some demonstrations on this, is that they don't necessarily behave how you might expect them to behave. So this actually this is related to the question that was just asked about, well, can you get an unbalanced stack? If you misuse these types, it's difficult to get an unbalanced stack, but you can still get things like information disclosure from the application. And I have samples of that I will get to right now, in fact. So back to the demo application. Here is an optimizations app. So basically what I'm doing is I am reading a line from the console, and if the line says exit, I'm returning and I'm echoing the line back out. My print message implementation is actually in native code. This is demonstrating p-invokes, and it's literally just a call to printf. There's really nothing terribly special here. It's a typical DLL export and then a DLL import on the managed side. So nothing. There's no magic under the rug here behind the curtains. If I run this, I can say hello. It prints out hello. Let me zoom in a little bit so everyone can see it. This is a secret string. Reflects that back out. Hi again, and so on. Like there's nothing terribly interesting going on there. The application behaves as expected. Now, in .NET Core, we introduced something called span and memory. And what span and memory allow you to do is take a little bit tighter control over how allocations take place. Let me actually comment this out and pull up the span equivalent. Oops, one sec. That's right. Yes. So this is similar code, basically, only it uses span instead of string. Sorry, need to comment that out. There we go. Perfect. So this uses span instead of string. And what it's doing under the covers is it is renting a character array from the array pool. It is reading character by character from the input, anything that's basically not a control character like a carriage return or line feed. It's putting that into the scratch buffer. This is still bounds checked. Even though I'm renting a 1 kilocharacter array, if I go past 1,000 characters, this will throw an index out of bounds exception. So there's still type safety here. And then what I do is I say, okay, let me now slice the span and then pass the span into print message. Print message is pinning the span, passing it to the print line routine, and then we're just returning back to the array pool when all is said and done. So run this, and it's the same print line routine in C that I showed earlier. Nothing has changed there. Hello. So I type that in, prints it back out. Great. This is a secret string. Prints it back out. Great. Hi again. Huh. That's rather interesting. So why is that? And the reason for that is twofold. First off, stack alloc and the array pool are not actually guaranteed to return 0 initted buffers. The array pool will literally return whatever the last thing that was returned to it. I'm sorry, when you rent from the array pool, it will give you an array that is the same thing that was the last thing that was given back to it. It doesn't bother clearing the data. It just gives you the array with whatever data it may have originally had. This is different than allocating an array from scratch, which is guaranteed to be 0 initted. Now, that in and of itself doesn't explain why the secret part was still being emitted to the console, because we're still slicing the span appropriately before passing it in. And that brings me to this part right here. We are pinning the span and then passing it in to an API that expects a null terminated wchar pointer. Now, remember, in .NET, strings are guaranteed null terminated. And by the way, if your string has an embedded null, like that embedded null will be seen as a null terminator here. Span, because span is pointing to a slice of memory, is not guaranteed to be null terminated. This API will actually just keep reading until it encounters a null terminator. In the case of the sample application, the null character wasn't seen until after it had already gotten through all of the data that was already inside of the rented array. And that data happened to be the secret data. This we actually have seen security incidents on as well. The typical example here is where you where you're processing some data for a user and you accidentally send that data to a response stream that data was not intended for. So you're contacting your bank, the bank accidentally sends you my account information instead of yours because there's remaining data left over in that buffer. Now, the final thing I want to show here is I type the word exit and it doesn't exit. What? It prints out exit and then the rest of the like slightly corrupted string. The reason for that is when you're comparing spans for equality, span equality is actually referential equality. What this check is actually doing is it's checking to see if this span points to the same memory address that this string called exit is contained inside of the application. Because this span is actually coming from the array pool, it's not a literal string, these two comparisons this comparison will always evaluate to false, even though it is even though the contents are the same using deep equality. This is different than if you're using a typical string, because the equals operator on a typical string always does deep equality, not just referential equality. So when you're dealing with spans, also remember to use sequence equal if you want content equality. Yeah, so that's if you're code reviewing code that uses the array pool, that uses spans, keep those things in mind. We've seen people get tripped up over that before. That's just some good stuff to know inside of your application. Again, this is just a summary of what we talked about. The final thing that I want to talk about, and I don't have time to do the demo here, but I will post the demo separately so that people can see it in their own free time. Be aware of how your application, if you are actually rendering it inside of a browser, keep in mind of how that data is actually going to be rendered. Normally, we talk about things like, okay, always HTML escape your data if you're including it inside of a tag or inside of the HTML body. Always URL escape your data if it's being included inside of the URL. And that's all well and good, but that's not actually enough sometimes. A typical example is if you're allowing if you have a forum where you're allowing a user to register their own username, and that username occurs as part of the URL, /users/my name here. What happens if I register a username that is dot or dot dot? Like the database, as far as the database is concerned, dot or dot dot are perfectly fine for primary keys. That username is fine, right? The database is going to accept it. But when I actually try rendering that URL to the page, it will be /users/dot dot, which is just going to take me to my application route. If I'm a bad actor and I'm now spamming your forum and I'm posting links to all kinds of malware sites, now your forum administrator might have the ability to ban my account by clicking on my user profile and then hitting a big friendly red button that says ban. But if my user profile page is /users/dot dot, you can't actually access my user profile page. Like I have actually slipped under the radar of the application. And as a result, if you want to scrub my account from the system, you probably have to get your database administrator to go scrub it because the web UI does not actually render the proper block button for you. Again, I don't have time for the demo. I hope that description at least summarizes it appropriately. I will separately record the demo and post it somewhere just because it takes around 10 or 15 minutes. And I wanted to leave a little bit more time for Q&A here. So if you wanted to mitigate those concerns, make sure that whenever you're rendering something in the URL, make sure that when you ingest that data into your system the first time, that you forbid characters that you never really intended to allow. It's never a bad idea to start off with allow only ASCII alphanumeric to begin with, and then slowly open it up if you decide that you need to allow more characters like dots, dashes, underscores, if you need to open it up for non-ASCII characters. If you're displaying links where people are able to put something into an ahref tag, keep in mind that you should validate those for well-formedness, that they're well-formed URLs, and they begin with HTTP or HTTPS. The reason for that is if I list my homepage as JavaScript::alert something, and there's a link to my homepage rendered inside my user profile, and someone clicks on that link, well, they're now executing JavaScript code inside the page. Like that is me XSSing other users on the website. And that's an XSS that can take place even though everything is properly HTML encoded. So yeah, that's actually all I had right now. I just wanted to leave a few minutes for any questions. Here are ways to contact me. I typed that correctly. I typed my name correctly. That's always a good sign. And by the way, this really only scratches the surface of the kinds of things that we look for. If you found this useful, please let me know. Let me know, especially if there's stuff that you would like to see in a future part. I have a Word document that covers like 3 times this much content, and there's just no way to fit it into a 45-minute presentation. That said, thank you all for spending the evening or your morning with me, and the floor is yours for questions.
I have a question. Are there any specific, I guess you could say, vulnerabilities in ASP.NET Core that only get invoked when it's running behind IIS with the ASP.NET Core module.
Are there any things that you have to be aware of if you're running inside of that environment?
Yeah. So like, if are there any I guess, have you guys run into any vulnerabilities that probably wouldn't be affected if it was running specifically underneath of Kestrel, but due to the way IIS processes modules, et cetera?
Yeah, I'm going through just kind of trolling through my recollection right now. There have been some issues where we had where we had some just flaws, failed checks internally within the web server, but those are things that don't normally concern applications, because remember the two buckets of vulnerabilities that I mentioned. The first is like there's just a mistake where we missed a check or something and we have to add it in. And the second is like, oh, this is actually something you, the developer, have to be aware of. All of the vulnerabilities that I can remember were in that first bucket. So to answer your question, like, no, there's nothing you would have to keep in mind that I'm aware of.
Yeah, that's good to know. Thank you.
Yep.
Any other questions?
Oh, I do have another question. And you stating that you have samples of this information. Outside of the samples, do you think, actually, are there any other resources for developers where they can look at kind of examples of things they need to make sure they have down so that they won't open these holes?
Yeah, so one of the things that we've wanted to start doing now that .NET is open source is the ASP.NET team has published some of their threat models. And in the slide decks, I actually have links to that. It'll be in the speaker notes. And again, this will be published, so you can refer to it after. So they've published their threat models for certain things, which I think if you're writing an application, it's very useful to see what they themselves believe the threat vectors are so that you can react appropriately within your own logic. We've also started actually mentioning publicly whenever we fix CVEs. So you can actually see both what the original code was and what the new code is. In .NET Framework proper, we never really advertised it all that much. You would basically have to disassemble the DLL. But now we actually mention in our issues like, hey, this PR addresses this specific CVE. So you can look for those same patterns inside of your own code. Does that help answer your question?
Oh yeah, definitely.
Yeah. I was, before I gave this talk, as I was preparing the materials, I was kind of hoping to look at other talks for some inspiration. And one of the reasons that I decided to give this was a lot of those other talks I mentioned earlier are focused really heavily on things like authentication, authorization, so on, and are very web technology specific, which is all well and good. Like those talks are extraordinarily useful, but they only really are useful to an audience dealing with that particular technology. And I wanted to create something that was more useful to the general .NET developer, regardless of whether they were making a UI-based web service, a microservice, a library, so on. So given that there isn't really there's not really a large ecosystem of such talks to draw inspiration from, I'm kind of hoping that this can kind of lay the foundation for that.
Yeah, this was very, very useful. I actually think I need to go and look through some of my source code now, especially with a few of these vectors.
Yeah, this is, I guess my paranoia here is like it would be really embarrassing if like I actually checked in code into the product recently that contained any of these vulnerabilities. Like that would be a big whoops, but such is life.
One question from Steve. He says, great talk, thank you, and curious to hear your thoughts or recommendations for how to incorporate security checks for .NET into CI/CD pipeline.
That is a good question. By the way, thank you for bringing those chat questions up, because I actually can't see the chat window on my monitor. One of the things that we've actually started doing is we've started writing Roslyn code analyzers for many of these things. Things that will address common errors. For instance, I've mentioned stack_alloc earlier. If you call stack_alloc in a loop, that memory actually doesn't get reclaimed until the method frames unwind. So it's actually a very good way to Stack Overflow your application. We're introducing analyzers for things like that. And those analyzers inside new .NET Core projects are actually turned on by default. I do not have a link to that project inside the speaker notes right now, but I will get that link in there. That way you can go look at the upcoming analyzers that we're working on. One of the examples I gave near the end was comparing a read-only span of char against a literal string. I would hope that we could have analyzers in order to detect failure points like that, so that you see a compiler warning rather than just being surprised when your production application misbehaves. Did that answer that question?
Steve says, yes, thank you.
Great, glad to hear that.
All right, I think we don't have any other questions, Levi. Again, it was really inspirational talk, I believe. I think it was really amazing, especially you just showed us again the danger of deserialization issues. It's been the headache for a lot of people in the last couple of years when they get a little bit more popularity around the world. Yeah, thank you so much for joining us, and thank you so much for your great presentation. It was fascinating.
Awesome. Thank you for having me. And I will take a little while to get the slides and the demos cleaned up, and then I will give the package to you for publishing.
Awesome. I will publish that on our Meetup event page. All right. Thank you everyone for joining us.